So in this lecture we want to talk about Ramsey theorem, and so that will help us to prove Schur's theorem, right? So before that, going to the theorem and proof, I just want to give some ideas to create graphs from binary relations. So whenever you have a binary relation on a set, so what I mean by a binary relation is nothing but any subset, right, of A cross A. So this is a binary relation on A, we say. So any subset is a relation. So this is a binary relation, right? Fine. Now when you have a binary relation, then we can construct a graph. For example, suppose you take A is equal to some numbers 1, 2, 3, and your binary relation to be some 1, 2 and 2, 2 and 2, 3. Suppose this is. Then the vertices are the set A 1, 2, 3, and the relation is like it's a directed graph initially. So there is a 1, 2 here, so I can have a directed edge from 1, 2. 2, 2 means you make a loop. 2, 3 means you make another. So this is a graph, produces a graph. Suppose it contains 2, 1 and 3, 2. Then we call this relation is a symmetric relation, because whenever AB is there, if BA is available, then we will call that. So in that case, there is a reverse edge between any pair of vertices. Okay, I can't say any pair. Whenever there is an edge from X to Y, there is an edge between Y to X. So we say that this graph is undirected. So if a graph is undirected, then we don't need these directed edges to represent this graph. We just need only edges without arrows, and a loop can be also like this. Okay, loop is without an arrow, because anyway, so a binary relation with symmetric nature gives rise to an undirected graph, right? Okay, so if it is not reflexive, no problem, because whenever there is an edge between X and Y, there is an edge between Y to X. So that's an idea, right? So any relation gives rise to a graph. That is the first thing. Now let's go to the Ramsey's theorem. So Ramsey's theorem tells you any gathering contains 6 or more people, right? Then there are either 3 of them are mutually strangers. They don't know each other, right? Or what happens is 3 of them are mutually friends. They all know each other. So these two situation will always happen if there are 6 people, right? So we need to prove it. So I have to formulate this into relations and graphs. Suppose you have 6 people, right? So I denote these 6 people as 6 vertices. And now they're telling, right, we are forming a relation. A relation is nothing but these people are related when x is a friend of y, or x is not a friend of y. So, but you can see that this is a kind of relation that everybody is related, because either x is a friend of y or x is not a friend of y. And also, if x is a friend of y, definitely y is a friend of y. So that is a symmetry. So this is a symmetric relation which produces all the edges between the vertices, right? So no doubt that this particular graph, right, has all vertices in between. So I denote these, I draw all the vertices like this using a light color, right? So if you draw the light, if you connect all the edges, right, and so I connected all the edges, right, with all the connected all the vertices with all another vertices, because the relation I defined produces all the edges. Now the problem is I have an OR condition here. If x is a friend of y, I denote this relation by a red color. That means x and y are friends. Friends. If they are not friends, I denote it by another color. Suppose I have another 2 fellows, some z and k. They are not friends, but then because to show that they are not friends, I am making a violet color. Okay. Now suppose 3 of them are mutually friends. Then what is the meaning? Suppose z, k and y are mutually friends. That means y is friends, zk is friends, and y and k are friends. So that means there is a triangle of same color, right? Violet color. Now you assume, suppose I give this is some h. Suppose x, y and h don't know each other. Then what happens? Y, h don't know each other, and I have actually missed a line here. They don't know each other. So that means there also forms a triangle, but it's a red color. That means they don't know each other, right? So this is the idea. So, but is it always possible that there is a monochromatic triangle? When I say monochromatic, that means a triangle with the same color. So that is a question. Can we prove it? Yeah. So Ramsey's theorem, a special case, tells you that there are 6 people or 6 vertices, and all the edges are present, and if you color the vertices with either violet or red, then definitely you will end up with a triangle with the same color. That's what we have to prove, right? This is the formulation. So the proof is we follow by pigeonhole principle. So suppose we have 6 people, right? Now since all the edges are present, I am very sure that there are edges between these particular 5 edges are always present, right? Yeah. Now the problem is there are 2 colors. So if I say there is a violet basket and a red basket, so these 5 edges must colored by these two particular violet or red, right? That is, in another way, what I am telling is I am putting all these 5 edges into one of these baskets, right? Then we know by pigeonhole principle, you can see that the number of edges here is 5, which is greater than the number of baskets, which is 2. Then definitely there is one basket having 5 by 2 ceiling function, right? This is equal to 2.5, which you get 3. So if you don't know the pigeonhole principle of this fashion, it's very easy to prove also. Suppose each basket contain less than, I'm telling there are at least there is a basket containing 3 edges. Suppose every basket containing 2 edges, at most 2 edges. Suppose there is at most 2 edges in each basket. Then what happened? Then total number of edges will be 4, which is less than 5, because we have 5 edges. So that is a contradiction. That means there is a one basket containing 3 edges or more. So I'm just assuming, let it be the red color. 3 edges are red, right? Now the rest of them will be, I assume, violet. It also can be red also, but what I'm telling is there is at least 3 edges having same color, but I'm taking the worst case. Now if there is an edge between here, then I have a triangle, monochromatic triangle, right? This is my triangle. So I blocking that particular scenario by just putting a violet there. So I blocked that triangle. Also, if there is an edge here, then that also forms a triangle, this triangle. So I don't want that, so I block that also, right? But the problem is, look at these guys, X and Y. Are they friends or not friends? They must be. They must be either friends or not friends. So I must, if they are not friends, there must be a red line. That means there is a triangle. If they are not friends, there is a violet edge. That means then also there is a triangle. So in either case you will form a triangle, right? So that's the proof for this particular theorem. So whenever there are 6 people, either 3 mutual friends or either 3 mutual non-friends. Okay, now we'll go for the multicolor triangle Ramsey theorem. So that means, what is meant by that? So I think you remember complete graphs. So when I say complete graph on 3 vertices, that means every 3 vertices connected by edges. So if I say K4, that means there are 4 vertices, every 2 pair connected by edges, right? Right, so that is K4. And when I say Kn, that means there are n edges, and between every vertices there is an edge. So that is an idea. Okay, so just recall. So what is Ramsey theorem tells you that for each r positive integers, there is an integer n which depends upon r, such that if each edge of Kn is colored using R colors, then there is a monochromatic triangle. So in the previous case the R was 2 because I was coloring K6, right? Then I showed that there is a monochromatic triangle. So it is a special case with R equal to 2 and n equal to 6. So this n depends on the number 2. And if you just ask me about when R equal to 3, what is this n? I don't know. I mean, it's there, but being the moment, I don't know, right? And if you ask for R equal to 4, what is the n? Such that if I color the Kn by 4 colors, I get a monochromatic triangle, but I don't know, right? So that's the idea. But the thing is, you can exhibit, you can prove this, right? Whenever there is an R, there is an n. When if you color this using R colors, you will produce a monochromatic triangle. But this n need not be the least of such n, but I can exhibit such an n, right? Yeah. So in the case of least, that is a different question. Now, how do we prove this? So we start from, suppose there is R equal to 1, that is only one color is available, right? If there is only one color available, then what is the complete graph? If you color, you get a triangle. Trivially, it is a triangle itself. If you color with the, if you are only having one color, to get a triangle, you must color all the triangle with the same color, right? So K3 is the one particular, right? So for K3 there is only one color, then definitely you will get a monochromatic triangle. Right? Now you assume that you try to prove this using induction. So you assume that this is true for, I mean, R minus 1 colors, right? That means for R minus 1 there exists a number nr minus 1, right? You assume this. That means if R minus 1 colors, you color, what is your assumption? If you color the complete graph on nr minus 1 using R minus 1 colors, you get a monochromatic triangle, MCT, right? So this is your assumption. Suppose you color K nr minus 1 using R minus 1 color, then you get a monochromatic triangle. Okay, now we have to prove this is true for R colors. Now you color K nr, right? So I assume what is the, I predict nr is equal to R times nr minus 1 plus 2 for R greater than or equal to 2. So I assume this. This is my prediction. I take some number nr such that R is equal to nr minus 1 plus 2. So this is a number because, right? Yeah. So now I color my KNR using R colors. Okay, I'm KNR using R colors, right? So yeah, so basically what happened is N1 we have proved that it is equal to 3 because for a R equal to 1 that n1, that complete graph is, that n1 is 3. And using that, I can form an equation like this, right? nr equal to r times nr minus 1 plus 2. That means if you want to find n3 or something, and n2, then what happened? This is 2 times n1 minus 1 plus 2. So in this case, what is n1 is 3 minus 1 plus 2, so that is 2 times 2 plus 2, that means it is 6. So when n is equal to 2, you get 6. So that's what we have proved in Ramsey theorem. When you color K6 by 2 colors, there is a monochromatic triangles. So this way, this is a recursion that you can continue this. So, and I have to prove that this formula actually works, right? Yeah. So assume that I color KNR using R colors, right? So our assumption is, and now you assume that I have to prove this using induction. So I assume that this claim is true for r minus 1. That means if you color k and r minus 1 by r minus 1 colors, then I'll get a monochromatic triangle. That's what I wanted to say, right? So this is, we assume, right? Fine. Now let's look at KNR. So in KNR, I choose a particular vertex V, right? Then in KNR, how many neighbors for particular vertex V? I have, you can see that there are NR vertices, so surely there is NR minus 1 neighbors for a particular vertex V. NR minus 1 neighbors, right? Okay. So in each of these fellows are basically connected to this V, right, by an edge, because this is a complete graph. Now let's calculate what is NR minus 1. So NR is minus 1 is equal to, what is NR? R times NR, R times NR minus 1 plus 2 minus 1. So that would be, you will get NR plus 1. Now these many vertices are connected to V by a single edge, right? Right? Then these edges are colored by R colors. So these edges are put into R color baskets. Then what happens? Then definitely ceiling function of NR minus 1 by R, this is a number, we calculate this now. So this will be is equal to NR minus 1 plus 1 by R, right? So this is going to be NR minus 1, because, right. So what is this? Why do I calculate this? I calculate this because there is one color basket contains at least NR minus 1 edges having same color. having same, yeah, like a color basket, right? So the way color, that means they all have same color. So I assume it is to be some red. So I assume this is to be red. Then actually I get a collection of vertices, let me call, which is V0, right, which are incident to that many, the edges corresponds to the vertices where the red edges corresponds to. And if there is an edge inside this V0 which is red color, then I have a monochromatic triangle. So it is very true that this is a part of a complete graph. So the V0 actually forms a subgraph which is KV0. That means an induced graph from that, because they are all edges, they present all edges, and if there is one edge which is red, then definitely we have a monochromatic triangle. Suppose we don't have a red color, then that every edges in that particular V0 is colored by at most R-1 colors. Why? Because red is not there. Then I can surely say that it is at most R-1. Previously it is at most R, but now I can say it is at most R-1. But look at the cardinality of V0. What is the cardinality of V0? We just said that it is at least NR-1. That many edges are there, so that corresponds to that many vertices, right? So this V0 is at least NR-1. So we have already assumed, our assumption, our hypothesis was, when R-1, when we color KNR-1 by R-1 colors, there is a monochromatic triangle. So this particular set contains at least NR-1 vertices. So that forms a induced subgraph which is a complete graph, and it is colored by R-1 colors. So definitely there is a monochromatic triangle. So in both cases we have a monochromatic triangle, right? So you go through the proof once again and try to understand the proof. Okay, so I'm just stopping this video. We will be going through the proof of the theorem in the next session. Thank you.